mm, today's topic is hashing, but before I tell you what this hashing is, let me tell you something about the data that we want to handle in this part, right? So we are going to. So I assume that all of you know what's an editing. Right? It's called abstract data. It's a model of collection of all the data, and uh, we know this actually specifies what type of data that we are handling, and uh, on those data, what type of operations that we are going to do. Uh, that uh, uh, okay, in the lab class, it's a Hoffman coding. No, so C, as I said, like C, you have to keep up on your own. So you also, it's no one can teach you this kind of coding. So I'll instruct the TA to uh, do the coding without using heap. Okay. So no, no. So this type of so is it only for you, and what about the others? So the algorithm you knew, right? Okay, so I'll ask him to revisit the algorithm again. This Hoffman coding algorithm. So in the next lab class, I'll ask him to revisit the Hoffman coding algorithm again, and also with we'll do the implementation without using this heap. Okay, that will I'll take care of. Okay, so let's not move into some other direction. Let's focus in uh, mm, what let's focus on the topic of today. Okay. So it's an abstract data type. So what are these abstract data type? It's a model which tells you that specifies the type of data and also the type of operations that we are going to do operations uh, on those data. Right? Okay. Uh, Fine. So an example of one example of those data, a simple, like I can say the integers, let's say, for example, right? So I know the type of these data integers means like it's doesn't contain any fractional part. And also I know what are the operations that I can do on this data, right? Roughly speaking, right? I can addition, subtraction, division, and many other things, many other operations I can do, right? And also not just the integers from your we as we are familiar with maths integers, and also there's some data type in C also, integer data type. Right? So I can treat that one as an abstract data type, and I can specify what type of data are these, and also I like to specify what are the operations that I can do. Right? Other abstract data types you have also seen. This is just a very vague example. You have also seen the linked lists or the stacks, queues. These data types you have, abstract data types you have already seen, right? Okay, so the another simplest one is array, right? But today we're going to deal with, I think you must have seen this one also, but may not be in this particular format. Today we're going to see the abstract data type of dictionaries, what we call them, dictionaries, right? Okay. So what is this dictionary? So this is one another. In short, we call abstract data types as ADT. Mm. Dictionaries store elements so that is like I'll tell you, which is a very generic term. It stores elements. Right? I'll specify what elements are there so that they they means the elements can be located quickly using key, using something called key. So it's basically it's basically a element key pair. What do I mean? For an example, let's say the student records. Right. So you as a student, you have many things for student records. I have name of the students, which branch are you in, what is the year of admission, right? Along with that, I can store your what's the CGPA, like many other or even some other things, non-academic things, let's say address, right? So all these things together, I call them, this is the element. Everything together, it's the element. Okay, so I want to, this is one element that I want to store, but how am I going to store this? It's a quite a big thing. It's a chunk of data, right? this whole data, I can I can access this whole data using something called a key. Right? What is the key in your case? Any guesses? Yes. Yes. Roll number. Right. So every student is having a roll number. Whenever I want to, so we have a database that contains all all of these informations of every student. Right. Now, if I want to fetch data for a particular student, it's quite messy if I search it by name or many one of you have same name, right? Or CGPA, address, maybe even same. Year of admission, obviously, many students take admission in the same year, right? But this roll number is unique, right? I can access the whole data, right? I call it element, right? In terms of I can access those data through something that we call key. Okay, so that's the abstract data. That's the data that this dictionary data type, abstract data type, can have. It's a basically element key pair. Okay? So in our discussion, we'll not will not be thinking much about these elements. Only thing we'll care is about this key. What key is this? Right. And when I say key, right, so it's already assumed that along with that key, we have the corresponding element also, right? But I may not write the key element pair every time. Whenever I write a key, you should understand that there is a associated elements with that key. Okay. And what are the operations that we do in here? Let's say um, our main operation is searching. Right? So I give you a key. As I said, I want to fetch the data of particular students. So I have to search for that key element, which is the roll number of that student. Okay. And there are few other operations as well. Auxiliary operations. I can say what's the size of the data, size of the dictionary, how many total key element pair are there. Right? Or I can ask whether my dictionary is empty or not. Or I can say, let's say, insert in the dictionary, insert key element. Okay. Key along with the element I'll have. Right? Or I can say delete one particular key out of this. Right? But the searching and these are the operations that helps me maintaining insert and delete, that actually helps me in maintaining the dictionary data type. Okay. And searching is the most frequent operation, generally most frequent operation that we do. Okay. Any questions so far? Okay. So now let's see how to implement uh, uh, implement implementation of dictionaries. Right. So one of the naive way of implementing is by, let's say, using unordered sequence. Unordered sequence. Right. So what do I mean by unordered sequence? I'll put each one of these, like all these uh, key element pair, I'll store in the order in which they comes. Right? I don't want to maintain them. So basically what I can do, I can use a linked list for this. So I have this one. So I hope everyone is familiar with this linked list, right? No. So in here I have inside this part is, what is this? This is a pointer. Okay. This is a pointer which points to the next node, right? And in here, I have those key element pair. Okay. But as I said, I'll only consider that here I have the key, right? The key is the most important thing. Along with that, whatever element that you want to store, you can store there. Right? Here I have key. So this is an unordered way. So I have arranged them in an unordered fashion. Okay. So now, can you tell me if I arrange them in this way? So suppose there are in total size is n. There are total n key element pair. So can you tell me how much does this take searching for a specific key k? K is the key here. So L means this linked list, I am naming it just A. So this does what? This searches the key K in the linked list L. Can you tell me how much time does this take if I want to search for a specific? Yes, O of n, right? Because these are unordered. Right? Or let's say I can, how can I do this? Is one more thing. Let's say I want to delete one specific key there. Right? This actually deletes this. How much does this take? Deletion. If I store them in an unordered fashion, this will also take me O of n, because for deleting, First, first of all, I have to find that one and then I have to delete it. Right? If I tell you that this is the particular element you want to you have to delete, only the deletion portion can be done in constant time. If I go to that particular node, after that, what remains is a constant amount of operation. But for deletion, you have to first search for that particular key and then delete it. Right? So that's why I'm saying it will take often time, right? But let's say for insertion, so deletion is the list, in the list it will be this case. So insert an element there. So how much time would you think this insertion will take place? Remember that I am just inserting in an arbitrary fashion. It's just a unordered sequence I'm maintaining here. Can you tell me how much time it would take? Uh, why do you think it's going to take O of n time? It actually will take O of 1 time. It's I can store it there at the beginning. It's constant time, right? Still, I'll maintain them in an unordered fashion. Okay, inserting at the head, and also I can insert at the end also, right? For that, only one thing I have to keep checking. I have to maintain a rear pointer also. It's a front and rear, right? Just like a queue that you have, right? Okay. So we can see the searching, insertion, and deletion. These are the operations that will take. Searching and after the node. No, I didn't say that you have to insert the key after a particular node. No, I didn't say that. I just said that insert one node in this list. I leave it up to you. You have to do it efficiently, right? So you can insert it at the very beginning or at the very end. It still you can do in constant time. Okay. So this is what the situation is when I have unordered sequence. Right? Let's say, suppose I want to store in an ordered fashion, ordered sequence. Right? Like for simplicity, you can assume that it's all of them are stored in an array. And array means like, let's say, increasing order of the key. Right? So can you tell me then how much time do you take for searching? Yes. For searching, it will take, let's say, I say array A, that would take log n time. It's basically binary search that we have seen. Right? For insertion, inserting a key K, how much time would you take? No. Insert cannot be done in constant time. Or think about the deletion first. Deleting an element. Those will actually take, both of them will take O of n time. Because, so for deletion, you have to search it, right? So you have this array. Suppose this is the particular element that you are looking for. You search for that, right? You got there in log n time, let's say. But when you delete it, from there, then what do you have to do? Not just deleting, removing that element. All the other elements you have to move one step before, right? And that will cost you O of n time. And the same thing will happen for insertion as well. Okay. 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 Fine. So, so this is something like I have much more time. So O of n and in some cases O of log n. Right? Uh, I can think of some another way of direct something called direct addressing. I'll tell you what that is. So suppose that we know that we know the keys are within certain range, within let's say 0 to R. Okay. Suppose I know these keys are of this form. Right? And I have, so what can I do? I'll consider an array of size R, and the elements that you want to store, that's much less than that R. Right? So you have such a big thing. Right? Uh, it's all the way up to R, 0 to R. Right? And these are the, and whenever you have, let's say you have a key of 10, you put it at the 10th place. Right? Now you see another key 15, you put it at the 15th place. Let's say, like this. Right? You see a key, something like this. So you can, for an example, you can think these keys are the telephone numbers, let's say. Okay. Usually we have how many digits in our telephone number? Let's say 10 digits I have, right? Each of them can be, each of these can consist of, let's say, 10 different digits. So how many different phone numbers can I have? So I have 10 digits, right? And each of them can have 10 different values, let's say. Yes. So in that case, it will be something like 10 to the power 10, right? And let's say in a city, I have, let's say, 20,000 phone numbers. 20K means K also stands for key. So let's say in a city, I have 20,000 phone numbers. Right? So what I do, whenever I see one particular number, I insert it in the right position of this array. Right? So suppose I do that. So what, how much time this searching would take? Yes. So it's an array. I can access any of these elements. So searching would take me. So, so wherever I have a particular number, I have that number in there, right? and all the other things are empty. Everything else, every other cell is empty. Right? So it might look like something like this. Right? Here in these places I have a certain key, but all the other places are empty. Right? Yes, the searching would cost me one, right? Constant time. Deletion, I'll search it and then delete it. That would also cost me one. What else? Insert an element in here. That would also cost me one. See, all of these I can do it in constant time. It's very good thing. So that's ideally what I want. But there is a major problem with this. Can you see what this problem is? Or let me tell you, please. No, there's nothing called collision in here. There's no collision in here. It's a wastage of memory. That's the problem here. So all the keys are different. All the keys are distinct. Right? I'm putting them in a huge array. Right? So as for our example, the value of R is 10 to the power 10. Right? So I have used an array of 10 to the power 10 size. Right? But only a fraction of that small fraction of that array we are using to store the elements here. Only 20,000 phone numbers we have in that city. Okay. So you understand the drawback? So ordered, unordered case, like few operations are taking much time. Ordered case also much more expensive operations we are doing. In direct addressing, we are doing all those operations in an efficient way, but at the cost of memory. Right? Memory is a costly thing. Right? So what's the way out? Okay. So that's where this hashing comes into picture. We'll use the idea of hash table. Right? What is this? So I have an universe of the key. Right? And from this universe, this is the let's say these are the elements that I want to key element pair I want to store. So I want to store them in some table. So what's the universe of the table? For our previous example, it's the universe is of size this much, right? And what are the elements that I want to store in here? These are of size 20,000, something like this. We are in this situation, right? So what we'll do, we are going to use some function. So I want to put them in a table. Okay, let's say this table is of size m. Table of size m. Right? How are we going to put these keys in that table? For that, we're going to use some function here that will take a key. that will take this key and map it to somewhere in the table. So it will take this one and map it to this one. Let's say it will take this one, map it to this one. This also goes to like this. Okay. This is what this function will do. And this function, we call it a hash function. Okay. So for our example, so one example of, hello, am I audible? Okay. Okay. So I think my screen, can you see my screen? I think it's frozen, no? So can you see what I'm writing in here? Okay, okay. Just let me share it again. Okay, it's fine now. Okay, so this is what we're going to do. So we'll take each of these keys and using that hash function, I'll take one function, I'll call it hash function. I'll map that element to a particular slot in my table, right? For our example of the telephone numbers, right? So it's a 10-digit number. For example, let's say I take 937252913. Right. So let's say something like this. And then 82112. And let's say these are the numbers. So one hash function, I can say, like, for example, a hash function, I say it's a modulo 100. Right? So if I use this hash function, where does this element go? Under this hash function, this will go to, what's the modulo 100 of this key value? Modulo 100 of this key is basically just the last two digits, right? Modulo 100 of this one is the last two digits, 11, something like this, right? Okay. So what is the size of my table? So it is 0 to one. How many slots are there in my table if I am using this hash function? Are we having, hello, anyone? N minus one? No, I'm not. It's I don't have all those things with me. So I'm fixing the size of my table, right? I'm fixing the size of my table to be M, right? I want to know the value of M. So it's basically 99. Based on this hash function, I can tell no matter what key value you have, if you hash it, this value will go to some one slot of this on this hash table, right? So this number here will be mapped to the slot number 23. This one will be mapped to the slot number 11, something like this, right? I'm not assuming that we have uh, enough space to store all of them in different locations. If I do that, so uh, it may not be obvious, but we will be actually losing in terms of operational cost. Okay, fine. So that's the hash function for you with this example. And now, obviously, you can guess there is some problem. There is a problem of something that we'll call collision. What is this collision? It's basically more than one key is mapped to the same slot. Right? That's the collision. For example, let's say all the phone numbers where I have the last two digits same, let's say all of them are having 23 at the very end. Right? No matter what is there at the beginning, right? All of them under that hash function of modulo 100, all of them will be mapped to the slot 23. Excellent. Wait. Yes. So what I was saying is like what is a collision? Collision is basically many key elements, many key, more than one keys are mapped to the same slot in the hash table, right? Then that's a problem. Why? Because then what? So how can I store them in this one? How can I store uh, two key elements in the same slot? That's the problem. Right? But suppose this problem of collision doesn't appear there. Right? Then how am I going to search for an element? Suppose I have all the database of these, all the of these phone numbers are stored there. Right? Suppose I want to search for a new number. Right? Then what should I do? So if I have a new number, I want to search that number in that one. So I will be I'll be using that hash function of modulo 100. That means basically I look into the last two digits of the number, and in that table I go to that particular slot and I'll see whether that element is there or not. If it's not there, if I want to insert, I can insert it, but I can delete that particular element also. Okay. So how much time does that take? If I don't have any kind of collision, right? Suppose we are in a nice situation that there's no collision in there, then can you tell me how much does this searching will take? Yes. Searching, insertion, deletion, all of this will take only constant time. That is what we actually want. And also, we have not used an arbitrarily large memory also. Yes, it's a not very arbitrarily large memory, but it's a kind of manageable memory we have used that is also cost efficient. And at the same time, if there's no collision occurring, then I can do all these operations of searching and inserting, deleting. I can do it in constant time. Okay? But I cannot guarantee that my data set will be such or my hash function is such that all the key elements will be mapped to a different location. In fact, that would never be possible. Suppose I have, let's say, 100 elements to insert. The number of elements that I have is 100, and the size of the table I have taken to be 50. Right. So, and I want to insert all of this. So that means that in this situation, that means that there must be collisions, right? Okay. So now the question is how to overcome this collision. How can I overcome this collision? Right? And this answer is something called the technique, we call it chaining technique. Right? What is this chaining technique? Chaining technique is something like this, that we'll see another way of resolving the collision, that's called open addressing. That will not in this class, but maybe in the next class we'll see the open addressing scheme. Okay. Um, so let's say this is my hash table, something like this. Okay. And let's say uh, both these K1 is coming in here. Let's say after this hashing, this is coming in here. So earlier I was storing this K1 in the hash table, right? Okay. Now, if I have another K1 and let's say this slot is let's put some, the slot is 75, right? And K2, I have another key that also comes in the slot 75. Then there's no way that I can insert it there. Okay. So what is the way out? The way out is that I'll not be storing the key elements on this table. Rather, I will do something different. So in this table, I'll be having a pointer to a linked list where I will be having these elements. You understand what I'm doing here? So first K1, uh, that's this table is now not storing the key elements there. There's no key elements on this table now. Rather, this is a table of pointers. They, each of these slot is actually pointing to a linked list where in that linked list I am storing the key elements. Okay? This is where I'm storing the key element, and these are basically pointers to that linked list that store the key elements. What's the property of these key elements? All the key elements. All these key elements under this hash function goes to this particular slot. Right? All these elements under this hash function goes to this slot 75, for example. Okay, so in this way, I can store uh, as many elements I want. Okay, you understand? Okay, so now let's see that let's see the good case and bad case about this chaining technique. Suppose it happens that all the elements or the majority of the elements are going in a specific slot. Okay, so for example, uh, all the elements are going to the slot 0. Hmm? Then, then what that situation would be? That situation would be something like in that slot 0, I'll be having all the elements. So there'll be like in total there will be like n elements there. All the elements are going to this. And this is exactly like, and also I am not maintaining them in any order. This is the situation of unordered sequence, the case that we discussed at the very beginning. Right. The searching can take O of n time. Insertion can be done in constant time, but searching and deletion takes O of n time. Right. That is not what we want. Right. What's the other case? Other case is, so why is this possible that all the elements are going to, let's say, if majority of the elements are going to a single slot after hashing, then the hash function that we have used is not a good one. So then I'll change some different hash function. I'll change that hash function and we'll see whether that type of situation can be avoided. Rather, what's a good hash function is, can you guess what could be a good hash function? Good hash function is the one that distributes the keys evenly over the hash table. No, I cannot guarantee that there is no collision, right? If I have, for an example, if I have to store 100 key element pairs, but my table size is 50, then there must be a collision, right? But I'm not saying that. A good hash function does something like it distributes the elements evenly. Right? So, so we'll call that, I'll define something called, so, simple uniform hash function. So, okay. So it's the hash function that distributes all the keys evenly, that I'll call, it's a simple uniform hash function. Okay. So at this point, I'll also define something called a load factor of a table. So what is that load factor? And this is let's say it's a n by m. So what is n? N is the number of keys that we are having, and m is the table size. So n by m, I'll call it. Uh, it's a load factor of this, and generally we denote it by the letter alpha. Okay, so for that example, the load factor is, for this example, the load factor is 2. Okay. Now see what this simple uniform hash function does. I have a table of size m, and I have n many keys there. Right? It maps all of this. Right? Obviously, n can be more than m. So each of this will be having pointed to a linked list. There'll be another linked list with this. Like each of them will be. Right. Now I'm using here while mapping what hash function we have used. I have used a simple uniform hash function in here. Right. If I am using a simple uniform hash function, can you tell me what is the length of each linked list? So here is simple uniform hash function, right? It distributes, why call it uniformly, evenly, or you can say uniformly. Okay. So uniformly means like on an average, each of these slots will be having the same number on an average, roughly same number of elements will be there. Can you tell me what would be the size of each of these operations? Oh, sorry, size of each of these linked list? Yes, anyone? On it, so total I have n keys with me, and I'm saying that my table size is m. So all of this will be having roughly n by m many elements in there, right? On average. Okay. It's not always equal to n by m, but on an average, it will be n by m in elements. Okay. Now, suppose this is the situation, then can you tell me how much time does the searching will take? Let's say H is the hash table, and I'm saying it's a K. Uh, can you tell me how much time this searching will cost me? Hello, am I audible? Yes, I'm adjusting it. I'm adjusting the screen. But the question that I asked, like, whatever you can see so far is fine. So what I have said is like on an average, each of these list will be having um, size n by m. Now tell me what would be the cost if that's the situation, that's the hash table that we have, where each of these slots is having a linked list attached to it of size n by m. Then how much time does this searching will take? So do you think it's O of n? Why? Why do you think it's O of n? Yes, why do you think it's O of n? Yes. Now I think you can see my screen, right? So I want to search for this key element. So what I do, I'll apply the hash function to it. I'll get the slot, right? But in the slot, we don't have anything. So the how much time we're spending here? We're spending constant time for computing that particular slot, right? And then it's basically once I get that slot, the searching in that particular linked list, right? How much time does that take? What's the size of that linked list? It's n by m, right? So it will cost me O of n by m. Okay. Yes. So if it's an unsuccessful search, it's like roughly same, like whatever is a successful search, unsuccessful search, it's okay. Deletion, it's a deletion. Again, as I said, you have to search first. That will cost n by m. And once you go to that particular location in the linked list, you just delete it in constant time. This deletion will cost you also O of n by m. How much does this cost to insert insertion? So when I have this key, I have to always use this hash function and I go to the slot that this hash function tells me in which slot I need to insert it. And once I know that slot, I can just simply insert that element at the beginning of that linked list. So that actually cost me constant time. Okay. But remember what was our ultimate goal? Our ultimate goal was to do all these operations in constant time, right? That is what we wanted, right? Can you think, can you suggest something so that these all these operations becomes uh, constant? Can you suggest something? Hash map, it's a hash function, basically. Mapping is function. That's what they say. Like what we're saying is like using this hash function, or if I have this simple uniform hash function, then Searching will cost me O of n by m. Deletion will cost me O of n by m. Insertion will cost me constant. But can you tell me, uh, or can you suggest something so that these operations becomes constant? Another hash function? No, no. I will take the size if the size of the table is linear in M, then what can you say about M by N? Searching, deletion, insertion, all of this becomes constant time. Yes. The table is up to you. So if you see that you have, let's say, you have a data of size, let's say 1 lakh, right? Those many data you understood. So you can take a table of size, let's say 10,000. Okay. So that says that load factor of this table is 10 then, right? Some constant, right? Now, if you have some uniform, simple uniform hash function, then you can do it, all these operations in O of 10 time. That's nothing but constant time. You decide your size of the hash table based on the size of your data set. Okay, do you understand? Any question? Mm, okay. Uh, so although we have analyzed this using simple uniform hash function, let me just highlight that this is a very rare thing. Most likely it will be the case that you don't have any simple uniform hash function for you. Now, when you design a hash table or you uh, uh, choose a hash function, uh, let's talk something about that hash function then. So, what are the properties of that hash function that we want? So, first thing that I want, it should be computed in constant time. Okay. Uh, Another thing that I want is that it should uh, it should be something like the ideal thing that I want. It's simple uniform hash function, right? Uh, Distributes the keys uniformly over the table. But it's a very, as I mentioned, it's a very rare thing to have. Right? Also, we want something that minimizes the probability of collision. Right? So the less collision that we have, that will be good for us. And also, this is something I want, it's essential. It maps equal keys to the same slot. Your function should not be something like once you have this key, it goes to the slot 10, and sometime else this again you have this key using this hash function, this goes to 20. This should not happen. Okay, you understand what are the properties that I want from a good hash function? Okay, so I think I'll so the next thing that I'll tell you about is uh, how does this, so this hash function is basically a two kind of mapping, composition of two mappings. So we said, like, we in our example of telephone numbers, like, we have taken this keys to be the integers, right? All these keys are integers, telephone numbers, right? But in general, these keys need not be an integer. For example, the roll number, right? In the roll number, you have also the branch codes as well. Like, those are not numbers, right? Those keys, roll number keys, are not integer. So every hash function would be having two things. One is a hash code map that converts the keys to an integer, and this integer, those integers can be from a very big range. But the second part of the hash function will be having a compression map that compresses the range of those integers. Okay, so in the next class, we'll see a few examples of these hash code maps and those compression maps, right? That we'll discuss. And we will discuss one more thing, another collision resolution technique that we call open addressing. Basically, we'll see two different ways of doing this. A linear probing, another one will be double hashing, right? That we'll do in the next class. Before I close, do you have any question? Yes, any question? Okay, fine. Okay, okay, thank you.